Hey, what's up YouTube? In this two-part series, I'm going to go over how I created several water dripping effects using Niagara. I used different techniques, some are quite common, some are less common, some are CPU-based, GPU-based, some are precomputed, some entirely dynamic. All share the same idea though. I wanted to spawn water droplets on some kind of ceiling, could be a wet cave or something, right? Then I wanted to have these droplets grow over time, like they are slowly collecting water, and then have them fall once they reach a certain size. I also wanted to trigger some kind of splash event upon hit, and that's the tricky part, especially with GPU emitters, but I'll demonstrate a couple of solutions. That will be in the second video though. In that second video I will also mention a scriptable tool I made for one of the GPU Niagara system I'll explain, so it should hopefully be an interesting couple of videos. This first video though is a sort of introduction and covers simpler CPU-based examples. Now it is not a step-by-step tutorial and I won't go into too much detail, so it's best if you're already somewhat comfortable working with Niagara. Please watch my beginner to expert video on the Neighbor Grid 3D interface for a more gentle introduction to Niagara. Alright, let's dive right into it. So what are you looking at? Well, this is a CPU particle system, one I might consider precomputed and static. The way it works on paper is simple. I first spawn particles in a circle, I then do a line trace upward to project particles on the ceiling if any is found, else particles are killed. Next I do a line trace downward to find the ground, if any, and precompute the distance to that ground. Knowing that distance and assuming gravity is known and fixed and that's the only acting force, I can then very easily deduce a freefall duration, and thus know ahead of time when particles will collide with the ground, if there's any collision at all. The rest happens on tick, positions are simply computed based on the freefall time and gravity. The freefall time is then compared to the freefall duration to know if the impact happened, and if so, spawn particles upon death. And that's the gist of it. Let's see that in more detail though. Here I spawn particles at a constant rate, and particles are spawned in a circle. Upon particle initialization, I set the initial sprite size to 0 because I want water droplets to grow over time, starting from 0. Lifetime isn't really important and is used here just as a security measure, just in case something goes wrong, because I handle the particle's death myself. Next, this is a custom module and that's where the troubles begin. I first use a collision interface to perform collision queries synchronously on the CPU. It's a simple line trace, basically. So I trace from the particle's spawn position upward to try and find a ceiling. Now, please note that this is using CPU collisions, so the result depends on how you set up collisions. For instance, having quite a complex mesh here, the automatic convex collision generated doesn't create a collision that is visually accurate, if that makes sense. Now this could be tweaked to get a better result, but you get my point. Particles may not be accurately projected onto the geometry because projected onto that simplified collision mesh. To fix this, either split your environment and meshes into smaller sub-meshes that can be more accurately approximated with simple convex hulls. Or use complex collisions as simple to trace against each individual triangles. This obviously comes at a cost, this is not recommended, but for the sake of this video I'm going to turn this on anyway. Okay, back to this Niagara module. Having done that line trace, next I instantly kill particles that could not find a valid ceiling. I cache that line trace hit position in case a valid ceiling was found though. I also cache how big droplets may become before dropping from the ceiling. Next, if a ceiling was found, I project particles onto that ceiling position, and from that position I trace downward to find a ground. Note the tiny downward offset to prevent an initial overlap during the line trace, due to floating point precision issues. Now that line trace may not find a ground if there's none, or if it's just too distant. In that case, it's fine, I still assume the particle can fall from that ceiling. It's just not going to hit anything and eventually die airborne. But if a ground is found, I get the distance from that ground to the ceiling. Else I fall back to a made-up randomized freefall distance. And using that distance, I can easily deduce how much time this particle needs to be free-falling to reach the ground. Finally, there's a simple state machine going on in this particle system. A particle can be in a free-fall state or be stuck to the ceiling. Just two states, so a single boolean does the trick. And considering this particle was just spawned and projected onto the ceiling, it's for sure stuck to the ceiling for now, so false it is. And that's pretty much it for the spawn stack. Onto the particle update stack then. Here I have two custom modules, and you guessed it, the first one is used to update the particle when it's stuck on the ceiling, collecting water and growing in size, and the second one is to update the particle when it's free-falling. So here I increase the sprite size over time. Note that I get the particle's actual sprite size, but I don't set it yet. The result is, for now, stored in a local variable, okay? Next I check if that size has reached the maximum allowed size set during particle initialization. If so, I clamp the sprite size to that limit. Finally, if and only if not falling, meaning stuck on the ceiling, do I override the particle's sprite size with the one I just computed. Else, I just forward the sprite size the particle currently has in its freefall state, right? When working with some kind of state machine, it's important to only set parameters when you have the authority to do so. Here it's quite a simple one, just two states, but with more states it can become quite a headache, and you gotta be super cautious as to not override a parameter by mistake when working on the logic to apply during a specific state. Anyway, if not in freefall, I update the particle's position so that it's offset from the ceiling by some amount based on the sprite size. That essentially allows me to change the scale pivot point, right? Now you might do that in the sprite emitter here, but it's very useful to be able to control that programmatically. So this ensures particles grow from the upper edge of the sprite, if that makes sense. Else they would likely clip through the ceiling. Note the initial modifier here. Without it, this offset would be applied on the current position, and that would continuously translate the particle. It'd be a feedback loop, right? Thus, the scale offset is computed based on the initial ceiling position. Last thing I do in this custom module is to update the state machine, meaning if already in that fall state, well, remain in that fall state, else if not yet falling, we definitely want to have this particle fall from the ceiling if it has reached its maximum size. And so when this is eventually set to true, this will no longer have any effect because the position will just be forwarded. And same with this. Thus, this module will do nothing, and it's precisely what I want. I want this module to update the particle when it's stuck on the ceiling, and only then. And you guessed it, the next custom module is used to update the particle when it's free-falling. It has a bit more to it, but nothing too crazy. Bear with me. So if free-falling, I increment a value I called fall time, using the delta time. That's a timer for the free-fall state, basically. Note that this is not a particle variable we've seen yet. It's not set upon initialization, nor here, right? Yet I get that variable's value the first time this particle variable is used. And so that might throw an error, depending on the way this parameter is configured in this custom module. Variable initialization is super important in programming in general, so you might want Niagara to throw an error when you get a variable that hasn't been initialized yet. Or have it be initialized to an arbitrary value, usually 0. I most often prefer to initialize all my variables myself upon particle spawn, but you do you. Anyway, if that fall time exceeds the fall duration I precomputed during particle spawn, here, well, that means the particle has hit the ground if the initial trace did find a ground. Else it means the particle should simply die airborne. Note that I'm being cautious here. I ensure this may only be true if actually in the fall state. Again, working with a state machine in Niagara can be tricky. Anyway, the takeaway here is that there's no need to perform a line trace to detect a potential collision. Based on the initial ceiling and ground positions traced at spawn, I'm able to predict the time of impact. Now there are both pros and cons to this. It's somewhat cheap because traces happen only once per particle upon spawn. But because everything's precomputed upon particle spawn, a particle may no longer react to any dynamic changes in the environment, something to be aware of. Next, if free-falling, I update the particle's position. This may look complex, but it's not. Note that I'm not using gravity acceleration, nor solving any forces and whatnot. Again, this is precomputed, and assuming there's no dynamic wind or forces to apply, the ballistic trajectory of a particle is well known. It's just the fall time squared, multiplied by the gravity, halved, and that's it. I do also apply the same sprite offset I applied when the particle was stuck on the ceiling to ensure the particle smoothly transitions from its ceiling state to its freefall state without any hitches. So that's the freefall equation, super simple. Velocity can also be super easily derived. And again, same principle as before, if not freefalling, I just forward the current velocity. This module again only handles the freefall state, right? Next, sprite size. I first get the size the particle had when it dropped from the ceiling. That's the maximum ceiling size I set upon initialization, right? That's what causes the state to change. So the x component remains what it is, and the y component is scaled based on the vertical velocity, to stretch the particle. Next, if the particle reached the end of its freefall state, that's what I computed here, well, because the particle's position is based on that fall time, and because that fall time is incremented using a varying delta time, it may slightly exceed the fall duration, and thus the particle may slightly overshoot its end position. And that could be a problem if that particle just hit the ground. It could clip through and be underneath it. Thus, here I make sure the particle is indeed at the correct predicted end position based on the precomputed fall duration, not the incremented fall time. Same for the velocity. It's not that big of a deal, but I ensure the velocity is also the correct one at the time of the impact. Finally, if the particle reached the end of its freefall state, I simply kill it. So you might ask yourself why I bother recomputing the end position and end velocity upon hit if the particle is killed. Well, that's because upon death I generate a death event, so I want to forward the correct position and velocity to particles I may spawn with that event. That's a module only available to CPU emitters, by the way. It may ask for persistent IDs to be enabled because by default this ID is forwarded during the death event, but you can simply get rid of it. Most often you don't really need that ID, so that lets you get rid of that warning. Note that I use this boolean I initially set upon particle spawn, so that this death event isn't triggered for particles not having initially found any ground and thus simply killed airborne. I obviously want to spawn a splash only if there's a hit. And that's it for that emitter. So, to summarize, particles are spawned in a flat circle, they are projected on the ceiling using a vertical line trace. From that ceiling position, a second line trace is performed to find a ground. The distance between that ceiling and ground is used to compute the time it will take for the particle to fall from the ceiling and hit the ground. A simple boolean drives a two-state state machine. Next, if stuck on the ceiling, particles grow in size, until they are considered to be too big to be stuck on the ceiling anymore. At that point, the state machine is updated and particles fall from the ceiling. A simple timer is ticked while particles are in that freefall state to first know if the particle has reached the end of its predicted freefall trajectory, and if so, it is killed. Second, set the particle's vertical position using the freefall equation. Finally, when a particle is killed due to an impact, a death event is triggered to spawn extra particles. And that happens using a second emitter and an event handler. I simply spawn a random amount of particles when receiving a death event from that other emitter. And the way it works is pretty straightforward. You first add an event handler to an emitter. Next, you should be able to spot the generate death event in that other emitter of yours in this source list. So select it, switch this to spawned particles, and specify a number of particles to spawn on that emitter per death event happening in that other emitter, and randomize that count if you will. Finally, add a receive death event module and specify what you want to do with the data forwarded upon death. The hit location should probably be applied on the spawned particles to have them be correctly located, and the rest should likely be output parameters, so you're free to use them as you please on that event handler stack. Like in an add velocity module. Vector 2 is the velocity, So I get the speed at the time of impact to drive the splash particle speed as well, if that makes sense. And vector 3 is a hit normal, so I can use this as a cone axis to orient the splash. The rest is super straightforward. Gravity, solve forces, and tada! Splashes. Using events is the most simple way to create that kind of cascading effect, and it makes your life much easier by allowing you to split the logic into different emitters. There's the main water droplet and there's the splash. Now again, events are only available to CPU emitters, and CPU emitters do come at a cost. It's not necessarily a bad thing though, especially if you're heavily GPU bound. CPU emitters may almost be free in a way in that case, something to keep in mind. Here the CPU cost is somewhat low because the most expensive part, line traces, is done upon particle spawn just once. But obviously this makes that emitter react quite poorly to dynamic changes in the environment. So let's investigate a more dynamic solution. This particle system is almost identical to the one I just explained. This splash emitter is 100% similar, and this one only has a few minor tweaks to it. Upon spawn, I now only trace upward to project particles onto the ceiling. There's no longer a line trace to find a ground and precompute a fall duration. It's actually dynamic this time, hence why I use a gravity force and solve forces and velocity modules. Note that the gravity is only applied when the particle is in its fall state. Next, the update sticky module hasn't changed. The update fall module is a bit different though. Now, if falling, I perform a line trace from the particle's position to the particle's predicted position, based on the particle's current velocity and delta time. And thus I just apply that hit position if falling and if a hit is detected. The particle is also killed based on the same criteria. And that's it. That small change allows this particle system to react to dynamic changes in the environment and even support wind and any other effect. Note that the system is now quote-unquote much more expensive because line traces happen on tick. There's however a magic trick to almost get rid of that cost. This collision interface has an asynchronous method. That allows traces to be performed at a more convenient time, possibly on another CPU thread. I'm not entirely sure, but anyway, there's a few gotchas with async traces. It's asynchronous, so there's usually a 1 or 2 frame delay until you get the trace result. So because you get the result with a tiny delay, I don't think it's possible to use async traces during particle spawn. That's a 1 frame event, right? So you can't just delay the spawn event for 1 more frame while you wait for the trace result. Unless I'm mistaken. Second, you have to store the query ID in a particle variable per async trace, so it can be sent back to that function next tick. So in case you use multiple async traces, query IDs must be stored in a unique variable per async trace. Third, note that the first time an async trace is called, this node outputs the default values. So false, false, a 0 position, and so on. And that may mess with your logic depending on the way you do things. Thus, you may consider adding an extra check to see if that query ID is 0 and discard the result if so. Anyway, if you feel comfortable enough to work around those minor technical details and don't mind the 1 frame delay, always prefer the async function. It's almost free, at least compared to the non-async version that is definitely not free. Alright, now, this quote-unquote dynamic particle system is still not bulletproof. It now reacts nicely to a dynamic terrain, but what if the ceiling is also dynamic? Uh-oh. And sad news, that's not easily solved. What we'd like to do here is what we may call dynamic object parenting, meaning I'd like for that one particle here to be literally attached to that surface. And it's technically doable, it's 2024, nothing's impossible, even more so with a GPU emitter. I think there are tricks involving the velocity gbuffer to perform movement prediction, but that can be a bit complex to set up and far from being perfect. With a CPU emitter though, I fear Niagara doesn't yet have the tools to let you do this. And the reason is somewhat simple after all. There's no way to predict where that surface is going to move to next frame if it's going to move at all. Thus, there's no way to line trace towards where the particle should have been if it would have stuck to that surface, if that makes sense. Now, a possible solution would be to store some kind of object ID, triangle ID, and triangle barycentric coordinates per particle to support object parenting. With that information, you could somewhat easily reconstruct the attached position. And Naughty Dog did something like this. Very, very cool tech and a super inspiring talk. Highly recommended. Sadly, UE doesn't have an object ID buffer to perform this kind of tricks. I think you could still somewhat do this though, using a user-specified static mesh. You could get that static mesh triangle data and know where exactly a particle is located on a mesh, and thus update that position in real time and do some kind of parenting, right? But the idea with these kinds of environmental effects is to be able to easily spawn them pretty much everywhere you want. So having to fine-tune each particle system to work with a specific mesh would be kinda annoying. And the quote-unquote ceiling may be made up of many objects anyway, so that would not work. So creating a CPU Niagara system that supports a fully dynamic environment is complicated. I'm sure it's somewhat doable though, there's so much you can do with Niagara nowadays. And who knows, maybe there's a simple solution I'm simply missing. But I would argue we are leaning a bit towards over-engineering at this point. Supporting a dynamic ground? Meh, alright, why not? A dynamic ceiling though? Not so sure about that. That would be for a very specific use case, and at that point you could probably find a workaround just for that use case. I don't know, you tell me. Anyway, that's it for this video, that's part 1. Part 2 will be out very soon and will cover more dynamic solutions using GPU emitters and distance fields. I also mention a few tricks to mimic death events with GPU emitters, quite hacky but worth knowing. I will also do a breakdown of a scriptable tool I created to allow me to bake data into textures to help me create a very efficient and feature-complete GPU emitter. So stay tuned for that video. In the meantime, consider leaving a like and subscribing to the channel. Project files are also available as a tier 3 reward on my Patreon. Alright, thanks for watching and thanks to all my patrons for the amazing support. I'll see you in the next video, take care of yourself, bye bye!